PowerPoint. So let's start with that. So I have a number here, 1.41. That's what I wrote. And now I'm going to say, what is it? Is it a natural number? Is it a integer? Is it a rational number? Or is it a real number? So 1.41, is it a natural number? Well, you go, well, what are natural numbers? So you write it out. Is 1.41 in there, Vincent?
No.
No. Therefore, it is not a natural number. This here. Okay, so this is all review. Is it a integer? 1.41. And the answer is no. Let's write it like this. Okay. Now, Mr. Thomas mentioned something last time. This is an infinite set. This is an infinite set. This is infinite. This is infinite. Like they go on forever, right? But some infinities are smaller and some are bigger. So if you can put a set like integers, 1-to-1 correspondence with the natural number, then we can say that Z is countable. Okay, so it's an infinite set that is countable. So in other words, if I can do this, I am going to, actually we can establish it right there. You guys see this? All right, we just counted 0. Now we're going to count positive 1. That's our number 2. Then we're going to do negative 1. We got 3 elements in correspondence with the natural number. And we can keep on going. It's like this. I'm going to call this chair 1, 2. This one is 3. What I've done is I've established 1-to-1 correspondence with the natural number system with the chairs in the world. And there are infinite number of chairs in the world? No, it's a finite. But okay, a finite set is countable by default, but infinite sets are also countable. Maybe there's a planet where chairs just are, there's infinite chairs. All right, let's keep going. Number 4 comes in here, positive 2, negative 2. And we can keep going forever. Therefore, we can say that the set of integers is countable, even though it is infinite. All right, and then the problem is we can't set up a 1-to-1 correspondence with the real numbers. This whole business is an aside, thanks to Thomas. Thanks, man. Okay, let's keep going. Is a 1.41 in a set of integers, which is this thing here? And the answer was no. And this is integers. If you forgot already, because we are in an English class, and this is natural numbers. Is 1.41 a rational number, as in Q? And the answer is yes. And the reason is that this decimal it has 2 qualities to it. It is terminating. It stops right here at 1. And other thing is non-repeating. There is no pattern. Because this is actually, so let me put it down here. This is actually and then I do 4, 2, and I'm just putting random numbers. This is the square root of 2, this number. And this is what? Non-terminating means it's an infinite number. You can call this number 2. 2 is a finite number. 1.414 is a infinite number or non-terminating. This is a terminating non-repeating decimal. Therefore, it can be represented as a fraction by putting 1 right underneath it and 1 0 for each of the digits after the decimal point. And now what you have here is 141 an integer. So this is all review. Sorry for the math and physics people. And then this 100 is also an integer. Therefore, we have an integer over integer, m over n is not 0. So we have the definition. It's a fraction. Therefore, this guy is a rational number. Okay, and then here's the definition. Anybody remembers? Should I just write it again? Yes. Why not? What does this mean? In or belongs to integers where n is not equal to 0. Any questions? Remember, we will never look at this again, ever. 1.41, is it here?
Yes.
And how do I write this thing out?
There's like a supremum for any set. Oh, we do that. Oh.
It goes to, is this a number? No. Is this a number? No. It depends on the number system. You can create a number system and say R star. In R star, minus infinity and plus infinity would be a number. But we're not doing that. I just saw that somewhere, so I'm repeating the textbook. All this is saying is, let's just make this here. We're going to represent our real numbers. Here's our 0. What are the real numbers? Every possible point on this line is a real number. Okay, let's move on to my next example, which is I need, okay, let's do, I'm going to do 1 now. So we're done. Let's put this. Is 1 a natural number?
Yes.
Is 1 an integer?
Yes.
Is 1 a rational number?
Yes.
Is 1 a real number?
Yes.
Very nice. And then this guy starts around here. Rational, this is not a natural number and it is not an integer because it doesn't look like one of these guys. Literally doesn't look like that. All right, and then let's quickly do square root of 2. Is square root of 2 a natural number? No. Why not? By inspection, which is a technical term literally. By inspection, we see the square root of 2 is not in that set. Kind of, right? It would fall right here, right? It would be right there. Okay, is it an integer? Again, by inspection, no. Is it a rational number? And it's a trick question. And I am from Pakistan. In Pakistan, we believe that it can be represented as a fraction. No. Why isn't this a, I mean, why is 2 a rational number? Because 2 can be represented as a fraction. Why not square root of 2 with a 1 here? And the answer is this numerator, this denominator, both have to be rationals. In other words, this guy have to be, integers. Is this an integer? No. No integer, no integer, yes. Therefore, this m is not an int. Int is how we call it in computer science, right? All right, so therefore, square root of 2 is not, okay. So is it okay, so it's not a rational number for sure, right? Is it a real number? Yes. And why is it a real number? Because
It's in that range.
it is in that range. Or that
It's an element of that set.
it is an element of that set. It fits very good, actually. That's what you were saying. Yeah. Sorry. Excellent. It fits right here. Also, 2 is here too, right? 2 is, let's say 2 is right here. Sorry, this is getting bad. Natural numbers are rational, integers are rational, rational numbers are rationals, and what are the other kinds of numbers? Irrational, right? What's an irrational number? Let's go back to this. They are in decimal form, non-terminating and non-repeating. And then what are rational numbers? 5/2. These are in decimal form, non-repeating and non-terminating. And I'm going to terminate my discussion right now. Okay. This means if a decimal formulation, what is the decimal? 2.5? Yeah, why not? 2.5 to 0. Is that right? 5 divided by 2 is 2.5? Yes, they have, right? That's right. This number is non-repeating. Oh, sorry. If it is repeating and it's terminating, then it's a rational number. Sorry, nobody stopped me. And these two guys are irrational. All right. Are we done? We're moving on. Any questions? I wanted to do one other thing. Another way to represent R, this is the best way to represent R. There's another way. Oh yeah, this is another way. We can say R is a set that contains X such that X is in real numbers. Doesn't do anything, does it? Math majors, anybody else? Some notation. What kind of notation is this, by the way? It's a set. And the other name for this kind of set is, Ryan?
Oh, sorry, I was answering the first question.
Answer the first question.
Well, I was gonna say you can represent completeness axiom now.
Axiom of completeness?
Right.
Oh, okay. A set that, okay, very good. Yeah, okay.
I had to remind myself.
So X is
That's
such that it obeys, satisfies. So X is all numbers X, and then could we put here? I don't know. I'm trying to satisfy the axiom of completeness. That's the other way. Almost there. I think I made a mistake here somewhere.
Yeah, I mean, I guess just the set. I would struggle to put it in self-builder notation myself.
Yeah, you could say all X satisfies the axiom of completeness. Something like that.
A discrete class.
This is turning into a discrete math class.
Yeah, well, I remember taking discrete math at UT Austin, failed it 4 times. Okay.
It's awful.
Yeah, we had like some major people in the field as professors. UT Austin, don't go there for computer science. Okay, let's move on. Everybody's bored to death. Very good. Good. Yes, this is math 401. Maybe I should change that. Also, I'm teaching it again in spring. So send your friends and kids. Okay, now we could go over, according to my PowerPoint, the principal properties of piano. I just looked up the pronunciation. Piano axioms. Yes.
I'm so sorry, I have a question. What is the axiom of completeness?
Oh, that is, we will be doing it today. Axiom of completeness means that if you have a subset of a real number, if you have a subset of a real number that is not empty and it has an upper bound, it will have a sup, as in sub, as in supremum. We're going to look at that in a second.
Okay.
Okay, so if you have a subset of a real number and it is not empty, then, and that non-empty subset of a real number has an upper bound, then and the axiom of completeness says that this subset of real numbers has a supremum. The leftmost upper bound, it will have the smallest, and it will be either in the set or not in the set. Very good. We have approval. Let's move on. So let's start. We're going to look at a case where this is not true first. All right. So I'm going to write this complicated set. We're going to use A. I'm going to do color coding now. So again, for the non-science majors, I have an X. X represents what? All the elements of set A. A will be a subset of a real number. And then A is a subset of real numbers, but A itself consists of only rational numbers. So I'm going to put Q here. So what did I just do? I said A is a set because A equals this parentheses, these curly brackets. When you see that, we're saying that A is a set. A's elements are all only rational numbers. Yes? Such that, so this is such that, and then this is belong in, or in our case, we are reading it as X. All the X's, all the elements of A are rationals, which means they are terminating or repeating decimals, or they can be represented as fractions. Okay, so what's the next thing we're going to do? Such that if we square our little x, it will be less than 2. That's our first subset. The second set that we want to, should we draw it out first? Maybe not. Okay, let's try this one here. So I'm going to use blue here. So the set B, that's the name of the set. All its elements are also rational numbers, such that all of the rational numbers are, the square root of these rational numbers are greater than 2. Not square root, the square of these rational numbers are greater than 2. How do we, so now we're gonna draw. If you look at this and kind of just gloss over it, and if you don't use a paper and pencil, it's just going to, you're gonna go, yeah, I know what this is, and I know what this is. Well, maybe, maybe not. All right, so let's do this. We wanna do which side first? Let's do this side. Okay, let's do this here. Okay, less than, so my color scheme is going to be, what do we do with this thing? Let's simplify this. This is going to be the same. This is the same as okay. So we're saying that now that we have x is less than the square root of 2, what are we saying? That this set A is a set that contains all the rational numbers that are less than this irrational number, rational numbers that are less than this irrational number square root of 2. Because this is non-terminating, non-repeating. This is an error. Because what are reals? Let's just do that quickly. Reals are rationals plus irrationals. Okay, so another thing, the theorems about how many irrational numbers are they the same number as rational numbers? And is there a theorem like that where they proved it or they still haven't?
Something about compactness.
Compactness, okay. Compact sets. Terence Tao has already figured it out.
It's density.
Density, yeah, we did that where rational numbers are dense but not as dense as real number. That's, oh shit, no. Okay, let's keep going. Sorry. Okay, let's represent this. We want to represent, so let's do, so we have a cutoff here, and then for this one here, and again, this is again for those who have not done math in at least 4 years. And so sorry for those who just took a math class this morning. So we have B is a set of rational numbers such that all of these, this is the condition, all the rational numbers are bigger than square root of 2. Is square root of 2 in the set? In A or B? No, it just divides the number line into two halves. So we can think of square root of 2 as the cutoff. Okay, so I'm going to put, here we go. I need a black. Okay, another thing that the book does, this is from actually from Mr. Rudin. You guys struggle with Rudin? Rudin, the principles of mathematical analysis. This is from this guy. What he does is he puts the plus sign here. We could put it up here, put it up here. What am I saying here now? That all the rationals that are less than square root of 2, only the positive rationals are what we're going to discuss here. So is 0 a positive number? And the answer is no, it's a non-negative number. It's a non-positive number too. 0 is messed up, it's from India. Sorry, Aidan's relatives. I mean, Pakistan used to be India too before they switched it out. Okay, so I'm going to put 0 here. And this is where this set starts. I could use blue here. Here we go. Okay, do we have set A now? Between 0 and what do I need to put here? Square root of 2. And it's in black because it's not. And if you're taking notes, you could maybe put 2 lines here for B. So this, yes, question.
Isn't 0 not in the set, so wouldn't it also have a bracket or like a parenthesis word?
Also, this means that it's what you have here is actually, is that what you were saying? What we have, the set A can also be represented as an interval like that. This is A. But between 0 and square root of 2 are millions upon zillions of real numbers. Millions of rational numbers, millions of irrational numbers. We are only interested in the rational. So this set A, any of the rational numbers that are here are in the set A. Okay, and then where do I put the other one? What do I need to do here? Is there a, so all x's that are bigger than square root of 2, and the lines indicate what? This indicates a rational number. And between these two rational numbers are lots of other real numbers. Or which, yeah, I should say that, right? This is a line that is a real number line in which we indicate one of the real numbers that are rational with a bar like that. Okay, all right, so let's look at this set A first. Does A have, I'm going to put, so this is 0. Let's call, this is square root of, so this is 1 here. This could be, let's make this 2, 3, 4. Let's put 2, 5, 6, 7. That's one of the numbers here. Does A have an upper bound? So set A starts at 0, and 0 is not included. Because is 0 a rational number? Yeah, because we can put 0 over 1, and both of these are integers. So 0 is not in the set. Why isn't 0 in the set? Anybody? What indicates up here that tells us 0 is not part of the set?
It's be positives.
That number right there. So only positive rationals. So how many positive rationals are there between 0, which is not in the set, and square root of 2 not in the set? How many rationals? Mr. Yes.
Is it just one rational?
No, not me, as in. Yes, your picture will remind me. Jacob.
Just Jake. Is it
Jake.
just one rational or is it infinite numbers?
So the question is there just between two real numbers, square root of 2 and 0, how many rationals are there?
Infinite.
Infinite, always. Okay. Why infinite? Because there is a half here. Let's throw in some more. Anybody else? 1.4. Actually 4.1, right? There are so many of these. Okay. Is there a so there are infinitely this class is not going well, unfortunately. Let's keep going here. So there are infinite number of. Is there a largest rational number? Maybe this example was too difficult. Why isn't there? Because you can keep on going closer and closer to square root of 2, and you'll always find a rational number. So towards the right, there are an infinity of rational numbers. So there is no largest rational number in set A. Is there a smallest rational number in set A? No, because every time you go left, you will always run into another rational number because there are infinity of rational numbers going this way. All right, now let's go back. So we also have no smallest rational number in A. So set A has no minimum and no max. All right, let's do upper bounds. Does set A have an upper bound? I have some numbers written. Give me an upper bound, Emma.
2.
Okay, she went with 2. I'm going to go with 4. Somebody go with this weird number here. 2, 1, 5, 6, 7. That's an upper bound. All right. So I'm saying number 2 is the smallest upper bound, which is called LUB. Is 2 the least upper bound? This is a stupid trick question, as in. So is this bigger than 4? This thing is bigger than 4. This is an upper bound. 4 is an upper bound, which is bigger than 2. 3 is bigger than 2. 2 seems to be the smallest one. Are there more rational numbers here? How many are there? Infinitely many. Okay, so what was my question? So the infinitely, so we identified 2 and 3. Is there a least upper bound? Why can't we say square root of 2 is the least upper bound?
It's irrational, not rational.
It is irrational, not rational. Okay, so that is the only thing. If we had this here, in other words, if the set of rational numbers went from 0 to 2, where the endpoints are not included in the set, then 2 would be a rational number that is not in the set, but it is bigger than all elements in the set, and therefore 2 would be the least upper bound. Okay, so let's repeat that. In other words, all of these guys are called X, and 2 is an upper bound if 2 is greater than or equal to any of the elements. Okay, so let's go over this. Those who are really sad, I'm going to call out. Let's see, is Sophia, right? Are you sad? She's very sad. All right, Sophia. Is 3 an upper bound? And why is it? Why is 3 an upper bound? Because, repeat after me, 3 is bigger or equal to any of these elements. 3 is not in the set A, but it is an upper bound. It bounds this set. 2 is an upper bound. And let's say, not 2 here, but 2 was right there. Is 2 an upper bound? Because it is bigger than or equal to any element of the set A. And is 2 then the least upper bound? 2, not square root of 2. I just switched your set.
Yes.
Yes, because it is a rational number. Now I'm going to do this. Is 2 the LUB, least upper bound or supremum of set A? No, because it is not a rational number. That's all I'm trying to get here. Okay, now I think we could look at this set here. Set B, does it have an upper bound?
Why can't irrational numbers be upper bound?
They can be. A set whose endpoint is a set of rational numbers with a right endpoint, which is a rational number, will have an LUB, will have a supremum. If the endpoint is not a rational number, then a set that contains rational numbers will not have a supremum. And that is this case here. So in the case of rational numbers, a subset containing rational numbers, it can have a supremum or it doesn't have a supremum. It's not always the case, it will always. In real numbers, it's always the case. Because real numbers are both rationals and irrationals. Okay, very good question. So because Q does not satisfy the axiom of completeness. What's the axiom of completeness? If you have a subset that is not empty, has upper bounds, this is an upper bound, this is an upper bound, this is an upper bound, and the smallest of the upper bounds in this case is irrational. Therefore, this set A does not have a supremum. It has upper bounds, but doesn't have a supremum. It is not empty, but it does not satisfy this. How do we change this? If 2 was the endpoint like this, now this set of rational numbers has a supremum. Real numbers always satisfy the axiom of completeness. Rational numbers don't. Okay. All right. So I'm going to stop here. Should we discuss the other set? Yeah, let's do this quickly. Set B. Right now we have 2 here. Does set B have a infimum? Okay. Give me a lower bound for set B. Is half a lower bound? And the lower bounds also have to be rational. Is that true, Thomas and Ryan? They don't have to be, right, in this case. But for the supremum position, they have to be. Okay, all right, very good. So we can have, okay, so half is a lower bound. Is 2 a lower bound? Because what's the rule? The rule then switches here. We have all the members of set B, X, have to be greater than or equal to the upper bound. I mean to the lower bound. Okay. Does set B have an upper bound? No, it goes on forever. Because, oh, what the hell? I didn't put this in. Okay. I'm like, why is this? What about this guy? Does it have a lower bound, set A? Yes. Okay, it stops right there, only positive rational. All right, we've killed this goat. Now let's do some easy stuff. As in the same boring stuff, but super easy. Okay, sorry about this. And then we're gonna write out the definition, and I think then we're out of time. Oh, we have so much time. Oh, God. Okay. If only they taught math like this, it would take like 500 years to go over the whole material of mathematics. All right, I have a set called, let's see, 3 and 4. Let's write this. If I just wrote this, what kind of set is this? Set of real numbers, set of rational numbers, if I don't give you any other information.
Set bounded by 24, that's all you have.
Real numbers. So rationals, irrationals, everything are the endpoints in the set, Sophia.
Yes, no.
I confuse you. Okay, let's do this again. Are the endpoints of the set in the set A?
Yes.
Yes. Is 4 in the set? Is 3 in the set? No. All right, let's represent this. Here is our real number line. And oh, I have both the colors. I'm going to use okay, so this set contains what? Millions upon millions of real numbers, as in rational numbers, irrational numbers, integers, all that. Okay. And let's put 0 here, and I'm going to put 1 and 2 here. All right, let's do this. And this set we're calling A. Let's change the color here. So set A, does it have an upper bound? Anybody? How many upper bounds does it have? Infinity, right? 7 million and all of that. So this is an upper bound. Is 4 an upper bound? Of the 2 upper bounds that we are showing in this picture, which one is the supremum or the least upper bound, the smallest upper bound? The leftmost, Mr. 4. Is this supremum? So 4 is the supremum. So sub of A equals 4. That's the terminology. Is 4 in the set? Is 4 the maximum element of the set? Okay. What if we had it like this? So I would use blue here. Okay, how many upper bounds are there right now? I'm gonna put one more here. 3, yes? I'm gonna ask who's, oh, you were yawning, I can ask you. Vincent? Oh, you are feeling hot? Okay, so I'm gonna ask you. It's like, I have, my other 2 classes are freezing. They're like fridges. And you are not Sophia, but you're Zara, Miss Zara from Afghanistan. Very good. Beautiful country. We'll conquer it again. Okay. As an American, I'm still not done killing Afghanis. Sorry. Your people must die. So it's for the greater glory of my Christian God. Sorry. So where were we? 4, yeah, you can't make, you can't talk about Afghanistan anymore. We've moved on, Ukraine. So this ethics professor was telling me, don't compare Ukraine with Afghanistan. I'm like, what? He's an ethics professor, he's a pro-war ethics professor in the philosophy department. I'm like, great. We just need more of these ethical people who are teaching ethics. What the fuck is he teaching in this classroom? That war is great, Allah is great. Even though I'm not religious. Okay, so Miss Zara, how many upper bounds do we have on the blackboard for set A? It's always a set of numbers.
Set A?
Set A. How many upper bounds do I show on the picture there? And hint, yes. Go yes.
Set A?
Set A. Set A is right here. From
Okay.
here to here. All the numbers between 3 and 4, not including 3 and 4, are in set A. All these real numbers. So 100 bounds this set from the right, 7 bounds the set from the right, 4 bounds the set from the right. So which one, so is 4 an upper bound? Yes. So what's the supremum or LUB? Which is the smallest upper bound? The leftmost. Yes, that's Sophia. We moved from Zara to Sophia, yes. Very good. Is 4 in the set?
Sorry, I keep confusing.
Yes, it is round brackets, so it's not in the set. Does set A have, so when 4 was in the set, 4 was the max too, right? When I say 4 is not in the set, but it's an endpoint that's not included in the set, does set A have a maximum number? No, because exactly. So there are millions upon millions of real numbers that are pressing against 4. The infinite number of real numbers going to the right.
But 4 is still the supreme upper bound.
Yes, yes. 4 is,
Or
so 4 is not a max. 4, not a max. In fact, set A now, the way it's defined like this, does not have a maximum number. Because there are infinitely many numbers going to the right. Okay, now let's look at how many lower bounds, LB. Lower bounds are represented in this picture here. And this is set of real numbers. Chris.
There's 4 on the board.
1, 2, 3.
The one you also have 0.
0. Very good. All right. So we got 4. And then let's just ask the stupid question. Why was 7 an upper bound? Because all the numbers here were smaller than, do we have, I should write the definition today. Okay. So I'm just going to quickly say that 7 is an upper bound because all the elements of set A are smaller than 7. 4 is a supremum or a least upper bound because it's smaller than any of the other upper bounds. 4 is a supremum because it's smaller than any of the upper bounds. And 7 is an upper bound, 4 is an upper bound because the elements of the set are smaller or equal to those numbers. In this case, elements of A are not equal to 4, but it is the least upper bound. In this case, 4 is an element of the set. Therefore, this business here works. Okay, now I'm going to delete all this and let's write the definition before we run out. So all this for one line of math, folks. Where the hell? Here we go. I'm using this one here. No, it's not this one. We have what, 10 minutes, folks? How much time do we have? 5 minutes. 5 minutes. Okay, we can do it in 5. Okay, here we go.
I know it.
So this is from the textbook by Abbott, and this is the definition. I think we'll be only able to do upper bound today. Upper bound. Okay. The definition goes a set. So I'm writing the definition here of an upper bound of a subset of real numbers. And Ryan is smiling. You guys can do your homework. A set A is, anybody remember this from last 4 classes? This means subset. A is either equal to R or is smaller than R. It's a subset. So A is a subset of R. Okay. How do we represent that? this is our A, is this bit, and this goes on forever, left and right. So right, it is definitely a subset. We could also say that maybe the endpoint of A is in the set. The right endpoint is in the set, whatever that is. Let's put 0 here, maybe. So A is gonna be just, let's not put that in there. Okay, or the right endpoint is not in the set. Does everybody get that? And here, we don't know what and here, maybe the left endpoint, the lower bound is in the set, or it might not be. Yes, okay, all right. Is bounded above. So today what we are learning is this kind of stuff. You see this line here, and you can draw this picture for that line. Then it says is bounded above. What do I do now? Set A is bounded above. I could say B here. Okay. And also where else? Is A empty set? No, it's non-empty, right? What about this guy here? Math major, Ryan. Yes, are you happy with that? When it says it's bounded above, can I do that, or can I only have B here, but not this one?
You're asking if B over B is an upper bound?
Yeah, I mean, this B is in the set, the blue B is not in the set, and this is the endpoint, the way set A might be defined.
It's just an arbitrary variable that you're using?
Yes, B is any number. It could be 4. Let's say it's 4, and this could be 7. Can we use the endpoint as an upper bound?
Okay, yes.
Yes, we can, right? Okay, very good. All right. And then A itself is made up of small little a's. E little. These are the elements of set A, right? Okay. Now, what is the condition? Such that, so we've done this, and then the next thing is we need 2 conditions, right? This is the definition of upper bound. When is this B randomly picked as the endpoint, as the upper bound, and this B and many other B's going to the right? When is B here an upper bound of set A? When B is bigger than or equal to any element little a of set A, right? So how do we write that? We go such that who is sleeping A, all the elements of set A are smaller than or equal to B. For, and you know when I said all A's, you just write that over here for all A's.